Let's get started with lecture 14. So first, a brief review of what we did last time. So we wrapped up the chapter on oscillations by talking with first damped oscillators and then driven oscillators and resonance. So we focused on a special case of damping where there's a drag force that's proportional to the velocity. So that was just one of the various models of a friction or drag force. So you could have a force that's just has constant magnitude but has a direction opposite to the velocity, or like this goes linear with the velocity, or maybe quadratically. So we focused on this particular case because that's the case where the math is simpler and one can solve an analytical solution to the problem. So the problem, let's say kx minus kx minus bv, the drag force, those are the spring force and the drag force, is equal to ma. V is dx dt. The acceleration is a second derivative. We found that this has a general solution. X of t is equal to the initial amplitude, e to the minus b over 2m times t cosine omega t plus phi naught, where omega is the square root of k over m minus b squared over 4m squared. Okay. We also talked about driven oscillations, where you have an external force that also depends on time, and we discussed qualitatively the phenomenon of resonance, where this external force that you apply to your oscillator, if it has a frequency, so if itself is oscillatory as a function of time, and it has a frequency that's close or the same as the natural frequency of oscillations of your harmonic oscillator, then you can absorb energy from this external drive better, and you get larger amplitudes, for example. So then we started talking about waves, the general structure of wave phenomena. So we mentioned there are two classes of waves. So we had transverse waves, where you have a disturbance or a displacement that's perpendicular to the direction of propagation. So a typical example is just a pulse on a string under tension. Electromagnetic waves are also transverse waves, because the electric field and the magnetic field that fluctuate in time and propagate in space are perpendicular to the direction of propagation. We had longitudinal waves, where you have a disturbance, so maybe at some point it's more compressed, that again propagates in some direction in space. So the typical example is like a spring, where you take one end and push it and pull it, and there's some compression wave that propagates along the spring. Or sound waves, similarly, they're pressure waves in air. So in these types of waves, the displacement is in the same direction as the propagation. We talked a little bit about these for transverse waves, so whereas mechanical waves in a string, we talked about the velocity or the speed of propagation of the wave, which was the square root of the tension divided by linear mass density, mass divided by length. This was tension. And we talked about one description of pulses, for example, known as the snapshot graph, where at some point in time, just imagine taking a picture of your entire medium. So if it's a rope, for example, or a stretched string that carries a pulse, you just take a picture, and for every point in space, you see the displacement. So if it's a localized pulse like this, maybe in some region in space, the string is just flat, the displacement in the vertical direction is 0, and then maybe there's a pulse like this, and then again it's 0, right? So that's let's say this is, let me put the axis on the rope itself. Okay, so let's say that's the x-axis position in a space. We're thinking about a one-dimensional string, and let's say this is d, the displacement from the equilibrium position. So where the rope is just flat, d is 0. And this is a snapshot graph. Okay, so today we want to continue our discussion of snapshot graphs and how they change as time goes on, and then from this think about a dual picture called the history graph, where we focus on one point along the string and look at its displacement as a function of time. So a snapshot graph is fixed time at one instance in time. You look at all the displacements for all the different positions, and a history graph, which can be extracted from a snapshot graph, and knowing the wave speed, basically focuses at one point in space and tells us about the displacement as a function of time. Okay, so let's keep thinking about this. So imagine that's let's say this is a snapshot at t equals 0, right? And let's say the clock is ticking. So at some later time, so let's say t is equal to delta t, right? A certain fixed time has passed. I look at my string, where I take a picture of this entire system at that point in time. Well, what would I see? So I would see all the displacements moving forward by a distance v times delta t, right? That's what it means for the medium to support a propagation speed v. It means if you create a disturbance, t seconds later, it will have moved away from the source or from the initial position by a distance v times t. All right, so let's say, I don't know, let's say v times delta t, let's say, is this much, right? So then this point again moves by the same amount. This point again, this is the leading edge, this is the trailing edge. This moves by the same amount. So here we will have the same height as the maximum height. So our wave will look like that, or our pulse will look like this. Okay? And again, if the clock keeps ticking, right? So let's say at t equal 2 delta t, now another delta t has passed, and the whole thing is moved forward by the same length, let's say this much. So now from here to here, and now we move by the same amount forward, so again the same shape, so it looks like that. Okay, So we can, from one snapshot at one time, so if I have that snapshot at equals 0, because I know that this is a wave propagating to the right at constant speed v, I can, for any other time, extract and draw the snapshot graph, right? It's just, you just move forward this disturbance, all the displacements. Okay, so now you may say, well, I don't really care about the entire rope. I'm interested at one point. Maybe there's, I don't know, maybe I've painted a little piece of this rope, and I want to see how it's moving as a function of time at that particular point, right? So let's, for example, focus on this point in space over here. So if you draw that vertical line, well, how is it behaving, right? So let's say at t equals 0, what is the height at that point in space? So let's go over here. So suppose I'm focusing at this particular x right here. Okay, so let's say I want to draw the history graph, which is basically for that one point as a function of time now the horizontal axis is time, I want to see what the displacement is for that particular point. Well, at t equals 0, it's 0, right? At t equal delta t, so let's say I go here, that's delta t. It's going to be this height over here, maybe, let's say like that. T equal 2 delta t, it's here. So it kind of goes up like this until it reaches that peak and then comes down. So it's going to be the mirror image of the pulse shape, right? So it looks like that. And then once the time passes from here, it will remain 0 because the pulse just goes through, right? So in this region where it's coming down, so suppose, I don't know, it's somewhere here where this region has reached this particular point that I'm interested in. So now, let's say the pulse is somewhere here, for example. As you can see, as it keeps moving, the height or the displacement goes down as a function of time. So the history graph is basically looks like a mirror image. Right, you flip it around a vertical line, and now it's a function of time. All right. So let's take a look at some slides here. So that's perhaps a cleaner picture of what I was trying to draw, right? So every time a time delta t passes, you just shift forward your pulse by a length d delta x, and then from this we can extract the history graph at some given point as a function of time. All right, now so these are, let's say, the snapshots, right, for different times. As time keeps going, the pulse moves forward. If I look at the cross sections this way, right, that's fixing the position and looking at different times. So I see, for example, here it has this height, then it's a little bit less, so the height comes down and ultimately reaches 0, for example, if you focus at one point. So we can think of the displacement as a function of two variables, right? You can either think about putting all snapshot graphs together for different times, which is done here, or putting all history graphs together for different positions. So then that gives you a function of two variables, x and t, position and time, and you know the height everywhere along this string for all the times. And it's remarkable, so because the pulse is just moving at constant speed, knowing one snapshot figure is enough to extract the two-dimensional plot of displacement versus time and position. So we're saying full wave is described by d of x and t. Okay. Now, mathematically, the relationship is pretty simple. So suppose at t equal t naught at some particular time, right? D of x and t naught is d naught of x, right? That's one snapshot graph at one particular time. So the statement is that now d of x and t for arbitrary t will be d naught x minus v times t for a pulse that's moving to the right with constant speed v. So this captures the fact that the height or the displacement at later times is just the displacement at the initial time, but at a point that's behind it, right? So going back here, see the displacement of this point at time delta x is here. But if over here, I just go back by the same distance delta x, which is speed times time, I can find it, right? So you can read off the displacement for any point at later times by just looking at the displacements at the points behind it at the initial time, right? This thing is just going through. So to read off the displacement here at, let's say, time 2 delta t, I just go back by 2 delta t times v in this snapshot figure. And that's really d naught of x minus 2 delta t times v. All right, so you may want to get a piece of paper and for yourself play a little bit with these figures, just kind of the same exercise that I did on the notes. Just try to do it to gain more intuition about this connection. So this is a wave moving to the right with constant speed v. All right, so let's do a quick exercise. So get a piece of paper, pause the video a little bit, try to solve this example. All right, so I hope you found the history graph from this snapshot with known speed. All right, so what's happening? We're interested at this point here, x equal 8 meters. So at t equal 0, at any time before that, the displacement is 0, right? The pulse hasn't reached it. When is the first time the pulse reaches that point? When do we first see action at this point, 8 meters away from the origin? Well, the leading edge of this pulse should reach that point, right? The distance is, at t equals 0, the distance is 4 meters from 4 to 8. The pulse is moving at speed 2 meters per second, so it's going to take 2 seconds for the pulse to reach this. And then it just goes through, so we're going to see a flipped picture. We're going to see this shape flipped around an axis appearing after, because the heights or the displacements at this point will first be here, here, here. We'll realize all of these displacements as this is going through that cross-section. And when everything ends, when the whole pulse has gone through, well, this point, the trailing edge, must reach that point. So that's going to happen at t equal 4 seconds, right? Because the distance is 8 meters divided by 2, that's 4. So we're going to see a pulse, right, that looks like the mirror image, the flipped image of this. And starts at 2, that's when the leading edge hits the point we're interested in, and everything ends at t equal 4 seconds when the whole pulse just goes through that cross section. And that's when the trailing edge, this point, is reached 8 meters away from the origin. This is another quick question, so take a few seconds, pause the video, try to figure out the answer. All right, so we know the snapshot at t equal 1, and we're interested in the snapshot at a previous time, right? So what should we do? Again, we know it's moving with speed v equal 1 meter per second to the right. So we just have to now, because we're thinking about a previous time instead of a future time, we have to just push it back, right? Push it to the left. By how much? Well, what is the difference? So how much time has passed between -1 second and 1 second? Well, that's 2 seconds. So we just need to push this back by 2 meters, and then it's the same shape. It's going to be 2 meters behind. So at t equal -1 second, our snapshot must look like this, right? Because at t equal 1 second, 2 seconds have passed, and we must have moved forward by 2 meters. All right. So now we talked about just like putting one pulse, right, into our medium, which in this case is a rope or a chain or a string or whatever. And that's it, and then it travels. However, we can just keep putting pulses, right? You can keep taking like one end of this rope and moving it up and down. So you keep one up and down after the other, and in particular you can generate a sinusoidal wave, right? So you can generate this pattern where the entire rope has moved up and down by for some time kind of taking one end and moving it up and down as a sinusoidal function of time, and you generate this pattern that extends throughout the entire medium. So let's look at a simulation of this, again using the same simulation we used before. Let's look at slow motion. So previously we played with this pulse, right? Generated a pulse and stopped. So moved one end up and down, and you just generate this pulse that moves away from your source. Now imagine we do something else. So we keep moving this one end up and down. Let me, 1 second. Let me also get rid of this end so it doesn't get reflected and get complicated. So we imagine this is a really long string that just keeps going, okay? So now let's oscillate this one endpoint. move it up and down, and then keep doing this, right? So as the displacements propagate away from the source keeps putting in more displacements. So eventually, the entire string, whenever you take a snapshot, what you see a sinusoidal displacement function as a function of position. And we expect, of course, that if we think about the displacement of one point, so let's say you take, I don't know, some point, some distance x from the source along this string, again, it's going to be some sinusoidal function of time, right? Because of the general relationship that we derive. Like the whole thing, if you pause, right? So let's say the peak is here, the peaks are at these distances, and then you let it play for a little bit. So basically the whole thing shifts forward. It's the same kinematics. See, the whole thing got shifted forward. So these snapshots basically look the same, except the whole thing gets shifted forward. All right. So that's again looking at the two-dimensional graph. Like this is, let's say at t equals 0, you have this snapshot. A little bit later, this has moved forward. So now this 0 is over here, right? Now this 0 is over here. The whole thing gets shifted forward. And now if you look at, let's say, the displacement at one point as a function of time, you see it keeps going down, then going up again, coming down. So again, it performs sinusoidal motion as a function of time. Now, how do we describe this? Well, there's going to be some additional information coming from the speed of wave propagation. So we're saying if you focus at one point in space and look at the displacement as a function of time, well, it's just performing simple harmonic motion. It has sinusoidal motion going up and down as a function of time, and we know how to describe that. There's an amplitude, kind of how much it gets displaced from the equilibrium position, and there's a period, right? What is the distance between the peaks? How long it takes to complete a full cycle. Okay. Now, let's think a little bit about this. So let's take one snapshot. Now we're talking about so let's take one snapshot that looks maybe like this. And assume we forget about the boundary. So let's assume we forget about what happens at long distances. So we assume this thing extends from minus infinity to plus infinity. That never happens, but if you focus in some region in the middle, you don't really care about what's happening at long distances, so we can imagine the thing just continues. So this is x, right? The distance. This is the displacement. This is a snapshot. Let's say at, for example, t equals 0, right? At t equals 0, we just take a picture, and this thing extends in both directions. So first, there is a quantity known as the wavelength. Lambda, which is the distance between peak to peak, and the distance where if I take this pattern and shift it forward by lambda, basically it falls back on itself, right? This peak will fall on that peak, this trough will fall on that trough. So it will coincide with itself. So that's the wavelength, how much you should add to x to get the same thing, right? It's basically the period of this function as a function of x. So if x goes to x plus lambda, the displacement doesn't change. So d of, let's say, x plus lambda at some point, at any point, this is at any point in time, this is equal to 0, but that's true for any time, is d of x and t. All right. Now, if I think about the history graph, let's say for this point, so x equals 0. So let's say history at x equals 0. Now, my horizontal axis is time. Again, I'm looking at displacement. And what am I going to see? So the same thing shifts by speed v, right? It's moving this way. So a little bit later, I'm going to see these times over here. Sorry, these displacements over here, right? As time goes on, I see those. And then this is just simple harmonic motion. So the distance between peak to peak, the periodicity in time for this function of time is the period, capital T. But these two things are not independent, right? So basically, let's say it takes a time t for a distance lambda to go through, right? That's what happens, right? So as the time t goes on, again, this pattern repeats itself. So the shift must be the same as lambda, as the wavelength. So the pattern falls back on itself. And we know that the wave is moving at speed v, so lambda is v times t. So that's an important relationship that connects the wavelength and the period, right? So let's say what is from here to here, right? That's the same distance as peak to peak, so that's one lambda from here to here, from 1, 0 to the, not the next one, but the one after. Right, as you can see, if you shift it by this amount, this point comes to here and it repeats itself. And so at time t, again, if peak to peak is t, if this is 0, this is also t. Right? So time t is precisely when one full wavelength has gone through, and then we go back to the second 0. We see this height at this point. All right. So let's do a little bit more math. So let's say we know that d of x and t is d naught of x minus vt, right? So if I know the snapshot, so d naught of x is snapshot at t equals 0. So that snapshot, let's say, how does it look like? So I'm going to write it as, let's say, a sine function. So I'm going to write it as x. Let's say that's sine 2 pi over lambda times x plus some initial phase times the amplitude, right? So see again, if you, so this thing that we drew here, phi naught is 0. That's just the sine function, but you could have shifted it a little bit. You have the choice of where you put your origin. What point is x equals 0? And then again, in the same way that by writing omega as 2 pi over t, we ensure that when you add a time, capital T, to your time, you get a phase shift of 2 pi and you reproduce the same thing. Here also, if I add lambda to my x, I add a phase shift of 2 pi and I get the same thing. So that ensures the correct periodicity. Now, from this, what can I say about the d of x and t? Well, it becomes a sine 2 pi over lambda x minus v t plus phi naught. So let's expand this out. 2 pi over lambda times x minus 2 pi. I write lambda as v times the period, the capital T, and then there's a v upstairs which cancels out. So our general function of x and t that describes a sinusoidal wave moving to the right in a one-dimensional medium with constant speed v can be written as d of x and t is equal to the amplitude times sine 2 pi over lambda x minus 2 pi over t plus phi naught. All right. So previously for harmonic oscillators, we defined omega to be 2 pi over t, and we called it angular frequency. We can also define k to be 2 pi over lambda, and we call it wave number. This notation is a little bit unfortunate because we also had a spring constant which we called k, and it looks the same, but unfortunately it's a common notation. So from the context, yeah, we have to make sure we don't get confused with the notation. So using these, d of x and t can be written as a sine kx minus omega t plus phi naught. There's also a little bit of a different convention used in the book, so I'm going to stick with this convention. We basically have the choice of picking the sine and cosine, right? Because we have this arbitrary phase constant phi naught. So for example, for example, let's say if that's theta, from here to here we have theta plus pi over 2, right? So for any general phase, cosine theta, which is this, is the same as sine theta plus pi over 2, right? So that's really an arbitrary choice. I mean, because we have this arbitrary phase constant, we can pick either cosines or sines. And for some reason that I don't quite understand, but it's really arbitrary, in this textbook, the convention is that for a simple harmonic oscillator, we pick the cosine, and for waves, where you have a displacement that's a function of position and time, we choose sine of kx minus omega t plus phi naught. Okay, so that was a little bit subtle. So let's try to get some practice. Feel free to watch this part again and maybe think about it more. Yeah, it takes a little bit of practice and contemplation to get these connections between the spatial picture and the temporal picture, and then putting them together by knowing that your wave pattern is just shifting at constant speed in one direction. All right, so this is a quick question. Yeah, think about it for a few seconds, pause the video, and then we come back and discuss it. All right, so we have this wave. It's a sinusoidal wave on a string. It's traveling to the right. At this particular instant, the motion of the piece of string marked with a dot is up, down, right, left, or 0. Well, what is happening, right? So this whole thing gets shifted. If time passes a little bit, this whole pattern gets shifted a little bit this way. So at this point, we'll see the displacement of a point that's behind it, right, a little bit. So then it has to move up. Okay. Here's another example. So again, trying to visualize these, right? Again, that's one snapshot of a sinusoidal wave at t equals 0. So the crest is here. And then a little bit later, it moves over here, it moves over here, moves over here. And so see, we have to focus on the motion of, let's say, one point. So let's focus on x equals 0 and think about its motion, right? So this is performing simple harmonic motion, right? So as, for example, this thing moves forward by a quarter of the period, well, this reaches from the peak to 0, right? The full period will be going from a to 0 to minus a, back to 0, and back to a, right? So in a quarter of it, you go, the height of this point, or the displacement at this point, should go from a to 0. And if that happens, that corresponds to a shift of the crest by lambda over 4. And then for 1/2 t, this goes from a to minus, it's gone from minus a to a, so the crest is going to be here. 3/4 of t, this comes back to 0. So there's a shift, the first shift, which brings this back to 0, and the crest will be here. And ultimately, at t equal capital T, the period, this crest has moved forward by lambda, and then you realize the same wave pattern. Okay, so that's the relationship that we derived, which follows from this picture. All right, so here's another quick question. Again, pause the video and try to figure it out. Okay, so what is the period of this wave? So this is a snapshot picture, right? Because the horizontal axis is x, is distance. So we're looking at a given time at the pattern of the wave. And we know it's moving at 1 meter per second to the right. Okay. So to get the period, well, we can, for example, extract the wavelength, lambda. So what is lambda? What is the periodicity of this function of position? Well, that's the distance between two peaks, right? If you shift it by 2 meters, which is for the distance from 2 to 4, this peak goes on this peak, this peak goes on this peak, this trough goes on that trough, the whole thing falls back on itself. So lambda is 2 meters, which we can get by visually inspecting this and measuring the distance between two peaks, for example. And, well, lambda is v times t, v is 1, so t must be 2 seconds. Okay, so, yeah, so that's the general expression that we derived, and we're going to use this quite a bit. Yeah, the most important equation that gives us both the dependence on position and time for a wave traveling to the right. So the last thing I want to talk about today is actually thinking about the physical velocities of the different pieces of this rope along the string. So the question is how they move, right? What's the direction of motion, and also the magnitude of the velocity for different particles on this rope. So imagine again, this is a snapshot graph, right? This is a function of position, and this whole thing is moving to the right. So if you take one of these points, right, let's say this point, and then a little bit later, well, its height will be, or its displacement will be the displacement of this point that's behind it, so that's a negative number, right? And so it has a negative velocity, it's moving down, and because that slope is pretty large, yeah, it has the largest magnitude. Whereas here, a little bit later, basically the tangent to this line is 0. So a little bit later, it hasn't really moved up and down at all, right? In the limit of time going to 0, the ratio of how much you've moved down to the time is 0. It's proportional to the slope of the tangent to this snapshot figure. So mathematically, it's kind of easy to derive it, right? Because mathematically, it's really easy to write the equation for the history graph. We just don't change x. We treat x as a constant, right? If we're looking at one point, each point is characterized by an x, by a place along the rope, around the x-axis. So to get the velocity of physical pieces of the string, we just take the derivative of this general displacement as a function of position and time with respect to time, where we fix x, right? So velocity, which is transverse, right? It's perpendicular to the rope, to the direction of propagation of physical pieces of the rope or string. At some given point, we just fix x, we treat it like a constant. So the derivative of sine is cosine, the derivative of that whole thing with respect to t is just minus omega, so we're going to get minus a omega sine kx minus omega t plus v naught. One thing that's really important is not to confuse these two things, right? We have two types of velocities, if you wish. So we call the speed of propagation the speed because it's fixed, it doesn't change direction. But that's a really different thing, right? It's how fast the snapshot graph gets translated forward, right? So how fast the disturbances propagate in the medium. That's a property of the medium, and it's constant. It doesn't depend on time. Whereas this physical velocity of different pieces of the rope, again, every piece is performing simple harmonic motion in the transverse direction. It's moving up and down, and it has a time-dependent sinusoidal velocity, which we just derived. Okay, so this is a good place to stop, and we'll continue the discussion of waves in the next lecture.